the use of visual programming for pharmacokinetic and pharmacodynamic modeling and simulation. What's very special about this course is this is a course to do things with. In other words, just as you wouldn't go to a course on tennis playing or skiing or swimming or anything like that if you didn't intend to do it, so too over here, obviously just sitting and listening, the first lecture is going to be an overview lecture. You will learn about what some types of modeling are and how one can use them. But the real goal, and what I managed to achieve with some of the students last term, is for you to pose your own problem, to formulate your own model, and with my guidance, to carry out a simulation, so that this becomes a working tool for you. That's the goal. To ensure that this goal gets achieved with at least those people who are going to hang in there and put in enough effort to achieve it, the course is designed that I will give a number of examples as we're going along. I will teach you how to use a certain platform called Stella, and after you've hopefully absorbed this, you will not only formulate, but you will present your ideas as to what it is that you hope to accomplish, what you hope to model, and then, with a bit of assistance from myself, you will give a presentation on the model that you will have created as part of this course. So that's, in broad outline, what we hope to achieve. And so the first thing for you to do as you're listening to all the different things I'm saying is to make notes in your mind, or maybe on a piece of paper, how this might apply to something you're working on or are interested in. So you'll have your list of personal ideas, so that when the time comes, you'll be able to choose and to formulate. Any question? Claim that having tools available which allow you to do exploration, which otherwise would have been extremely difficult and tedious, is going to make a difference on how we attack problems and how we think about problems. And I feel that the modeling tools are going to be in the forefront of the sorts of things which are going to let people have better insights sooner and dynamic insights. So that's my pitch for why I think what you're doing is valuable and important. If only pause this thing. See births per year, population and deaths per year. You have here an ultra simple example of feedback loops from a central model component. In other words, there's a population. Everyone will agree to that. There are births per year which are being affected by certain factors which they fed in, which can be ascertained. Maybe the average fertility, the fraction of population giving birth. So there are lots of factors. They picked out some factors which they thought they could get a measure on. And obviously there are also deaths per year, which will be affected by the average mortality. And it's going to be different in all sorts of different parts of the world. How did they aggregate it? There are lots of questions to be asked. But conceptually, you can see where I could take just this little submodel and watch my population either growing or decaying based on various inputs. So this is the essence of a very simple model. And using that segment of the model, you then go on to what I have on the overhead, or what you have on the next page. Namely, if you take a look at the top of that next page, it says population with births per year and deaths per year, and fertility and mortality. In other words, what I've just shown you is one segment. And my methodology is such that you can do your modeling simply in little segments, and then test out each segment, then link them together, and then run them together, which may lead to some surprises, because when they hook up, they may not work as they work separately. And this world model, so to speak, captured what they considered the major aspects of what we have to be concerned with. their representation correct? Well, you can argue about it, but it's a way of capturing a lot of complex factors and linking them and looking at their dynamics, which can't be done easily with other tools. And then finally, here's a sample run on the next page. And as food per capita went up and industrial output went up, the amount of resources left over, which is your top line, started declining. And if that's the case, then eventually this decline will affect the amount of food available, and when that starts going down, and pollution is going up simultaneously with bad side effects, eventually your population will have to take a nosedive. And so that's the essence of this model. Views of the modeling process, okay? And I think what I will do is I will talk a little bit about the modeling process. This is from the math book, but obviously we're going to be doing all sorts of idealizations based on our experiences. And there's a neat quote that I picked up somewhere. There's nothing as practical as a good theory. In other words, if you think you understand something, even if you're wrong, it gives you some guidance as to do some building, as long as you don't get into trouble too badly. And so I'm going to go and talk a little bit about what I see as the steps, and then I'm going to do a little bit of the underpinnings that underpin the platform that we're going to be using. So let me stop that, whatever he's saying there. This is just another example of a simple model, and one of the, I may give one or two little assignments, and one little assignment is think up one or two topics that you'd like to model. Okay, so that's don't worry about it being realistic. Just, if you could, what would you like to do? All right, so that's a very simple thing. Number two, everyone here supposedly knows a little pharmacokinetics. Let's use these little arrows and boxes and draw a little diagram of a two-compartment system which only has outflow from the central compartment. All right? Here's a simple diagram with only causal loops, and there's some cell population. Some guy's looking at a petri dish or what have you, and he's giving it a certain amount of nutrients. The cells are replicating. They're giving out environmental waste. There's a certain environmental waste removal capacity. There's a certain amount of death, which to some extent might be affected by the metabolic waste. So here we have a moderately simple system where someone who's carrying out experiments and tracking what's happening in his petri dish might want to try and see what it's going to do for him. In general, every once in a while, someone comes to me with a problem, and I try and model it, and I have a number of stages that I go through, and everyone goes through. Number one, if you've never modeled, there's what in this book they call neophyte anxiety. In other words, you've never done it, you're afraid, but that's another problem. This is the world. I'm working now on there's a drug which is given for osteoporosis, and it turns out that they discovered in post-marketing, they approved it, that the number of fractures that resulted were fairly large, let's say, unexpectedly large, especially because the drug was effective. The reviewer looked at it, it was enhancing bone mass density, and so I was asked to look at it a little bit, see if I can model it. Well, I know lots of things, but I don't really know very much about bone structure and how it works. So the first thing, especially if you got a lot of references, is a big blooming confusion. All right? And what is it that I should look at? Not only that, even afterwards there's confusion that occurs, but for starters, what are the relevant factors? And even if I do a bunch of reading, there are many, many factors, most of which I'm going to have to discard. So I learned about osteoblasts and osteoclasts and the fact that the bones are being, and there are different types of bones. There's trabecular, there's other, and they react to all sorts of forces. How am I going to do any modeling? And the answer is, well, having identified osteoblast, osteoclast, the drug, and how its possible action might be, I'm getting started in that I have identified my elements. It's like, once you can put down your boxes, you are ahead of the game, so to speak. You at least know what's what. You know the ballpark you're hoping to play in. And so this is the early stages. Once you've picked your topic, the question is, what are the elements that you really want to look at? Are you looking at mortality questions? Are you looking at toxicity? Are you only interested in levels in the blood? Are you interested in effects on heart rate? And what are the main elements that you'd have to look at? Is it an organ? Is it an endocrine system that you're worried about? Having identified those things, the next question is, how do they interact with each other and with the outside world? So what are the hooks on everything? If I'm looking at lymphocytes, the question is, what triggers their growth, their proliferation, their death? If I'm looking at bone, well, what is triggering the activity of the osteoblast or the osteoclast? How are they going to react? So I have to find definitions of that, which is partly, we hope you will take some problem where you are an expert, so you won't spend a lot of time worrying about what the essence is. You at least will know something about it. Then the next question is, how do these things really interact? When you get to this stage, you're ready to start building your model. And in other words, if I assume that as bone density goes down, if there's enough calcium, then the osteoclasts are going to do ABC, I have my framework there. And so the early part of this course, all you have to do is do a little bit of identifying. And it's not necessarily as easy as it sounds, because the formulation of the problem is frequently one of the most difficult and critical steps. So this is part of modeling. Then you've reached here, you have it on paper, then you're ready to go on to simulation, namely asking, well, what if a level of calcium is higher or lower? What if the bone mass starts at a higher or with a greater, or what if I assume that the relationship to fractures is more or less? So then you're ready for simulation. And one of the main reasons that I do not start off this, later on I'm going to start earlier than I did in the other course, actually showing you things on the computer, because I can do things in real time and you'll learn from it. But I don't start my first lectures like that, because the essence of modeling is thinking about the stuff, and hacking at the computer is not modeling. All right, so these are the central themes of modeling. Having said this, I go back to our interactions with the world. You have, and I'm not going into detail on it, there's Appendix 1, which is a chapter from a book by someone called Bross, Design for Decision. And it's Chapter 10, which deals with modeling, and he has a few pictures in there which represent the process. There's nothing very profound. It's I don't know if I have this up front. It's definitely in the back in the appendix. And essentially, what Bross says is, And this was shown on the other page, which you have here, the real world and the physical world and your mathematical world. But basically, from the data and from your general concept, you're now going to go and create a symbolic model. This funny little book here for social scientists has something called steps in building. And they say, well, you need to be able to have some symbol. And you need some rules for manipulating the symbols if you're going to do anything in the modeling world. So, and my symbols do not have to be mathematical symbols. That's one of the points. I'm going to show you how you can drag around little boxes on the computer screen and hook them up together. And the manipulation is whatever you do with it, like you run it. And you're going to have to get some sort of values, either guess them, make them up, get them from data, I don't care. And your model is going to come out with certain results. Here's what it goes like. Well, hopefully you will have something in the real world to compare it with. Not necessarily the exact thing, something close, so that you can evaluate it and say to yourself, how good or how bad am I? Let's go down to the bottom one here. And after you evaluate it, you go back over here, evaluation no good. When I do modeling, I sometimes, especially since I do things sequentially, I build things up with more factors, and my models are small, I can do it quickly, I may go through 5 or 10 models till I get to one which satisfies my various requirements. That's just fine if the process is efficient, namely if it doesn't eat up all your time. Otherwise you can't do it. Again, in this nice simple book, it points out a formal or analytical model is going to implies that the question is important enough to you to invest some extra time as opposed to just top of the head. And so that eventually, hopefully, you will get a general evaluation that things are good, iterating between the symbolic world and the real world. So this is the general outlook of how we're going to do modeling. Now, with respect to specific tools, I think it's best to work with a very simple example. And so, everyone has a copy of the handout, I trust. Yes? Don't all answer at once. Yeah. All right, so essentially I'm going to be going through the handout right now. Of course, I misplaced my copy, but that's another story. I want to deal with a so-called one-compartment model with elimination. Thank you. As soon as I wrote this down, after I wrote it down, I looked at it and I said to myself, this one sentence makes a lot of presumptions. It presumes you know what I'm talking about. Well, what I'm talking about is we take the entire complex human being. See my complex human? Number one, I simplified the human being a bit. I also sometimes, because for equal rights, I sometimes make him female. So this complex human being is assumed to be one compartment. There's one well-stirred area in which everything is homogeneous and uniform. Obviously, this is I call this a heroic leap of simplification. It's unbelievable. But for our purposes, we know from experience that it's sometimes good enough. So one of the catches of modeling is you can do absolutely outrageous things, and sometimes they might be satisfactory. That's what a one-compartment model is. With elimination, this means we know that human beings, given all sorts of things which they don't incorporate into their bodies, they get rid of them. So we'll assume that for whatever drug I'm looking at, for whatever purpose, and it doesn't have to be drugs. I'm going to later on show my fishing example. It could be a guy fishing under certain circumstances. I'll show you which. So let's assume this is the model, and let's assume that I'm giving a bolus, because this is nice and simple. And my bolus means that essentially I fixed what I call my initial condition. I'm starting with a certain level, because it's assumed to be instantaneously. It all mixes instantaneously. It distributes instantaneously all approximations which may only work under certain circumstances. Therefore, when you're doing modeling, you better know the limitations of your model. So therefore, at time t equals 0, the amount in the body, I can call it A or A0, and it's equal to the dose, which I also am calling D. And there's a rate of elimination, which I'm calling R. All nice and simple. I now want to work my way through a few little equations so that you will understand the underpinning of what we're going to be modeling with and in, and what's going to happen when the computer is going to do things for you. The rate of change of drug in the body. So if the amount of drug is A, I'm taking in this equation, that's the next page, I guess. This was designed so that you could read it. I'm funny that way. I like people to. Okay, take the amount of time t equal t2, let's say 2 minutes, 5 minutes, minus the amount of t equal t1, let's say 4 minutes. So the amount at 4 minutes minus the amount at 3 minutes over 4 minus 3 gives me 1. The change is going to equal, since it's going down, this change is going to equal to minus the rate because the rate is a rate of excretion, a rate of elimination. So that's a simple way in a difference form of writing down what's happening. Is it accurate? No, it's not accurate because I'm taking it at 2 times. What if something is happening and it's curving? So I'm only getting a crude approximation. This won't bother me on the computer because I will determine my time intervals. It might bother me sometime because if I forget and set the time intervals wrong, I will not get a good approximation. Okay, so my T2 minus T1 is delta T. Let's assume they're all uniform for now. So instead of 2 and 1, I can have any I plus 1 and I. And that's my delta T. So my top equation can now be written just multiply through by T2 minus T1 or delta T. So my top, and take the A at the earlier time over. So I got A at T sub I plus 1, like A at time 5, is equal to A at time 4 minus the rate of change times delta T. Now, why is this a very good equation? It's very good because if I tell you the initial time, the initial amount at time 0, I can generate what the time will be at what the amount will be at any future time with this relationship. There is a catch. I haven't told you what R is. For simplicity, I might have R a constant, but R could be something complex, in which case we'd have other. But this is, so here's a simple difference equation, whose correctness depends on the size of your delta T, which captures what's happening. And it's fairly general. Why is this important? Among other things, this is important because from this formulation, if you took any courses in mathematics at all, you know that as delta T goes to 0, this is the definition of a differential equation. Let's get out my nice page that says that. It only says it, doesn't prove anything. But this is really the definition. As delta T goes to 0, I get my instantaneous rate. It's like velocity at the limit is delta x over delta T at the limit as delta T gets small. So that this will hold true exactly in some sense. So this is an exact capturing of some relationship with respect to rate of change. Now there is a catch. This is telling me that the change in amount is equal to this rate thing, but it doesn't give me the amount. If I have some complex expression, chances are I won't know how to integrate it to get what the amount is at any given time. So it's nice to write it this way, but what can I do with it? The answer is, I can learn integration, take a good course in calculus, but even then, not all functions are integrable. Or you can use my platform, which will do it for you. It doesn't solve all problems, but it does help. The other thing is, it's good to be able to think this way because you can then formulate your problems sometimes this way, so you have a language in which to formulate your problems. Having done this, I want to ask the question of the relationship, if you wish, between the differential equation and this difference equation form. There are people who work with difference equations, and there are books on it, and the system dynamics method is just a lot of difference equations. The big point being, if I'm working on a computer and I want numerical solutions, I'm going to take little increments of time, and I'm going to take these approximations, and I can grind my way forward. You can also do it by hand. When I was in graduate school, I had to do one of these by hand. But it's sort of painful. So if my, found a little error. If my t or my delta t goes to, it's my delta t, which is this is supposed to be over here. I proofread it, but not perfectly. All right. My delta t goes to a small amount, not 0. I'm not going to the limiting case. And so the equation that you just had before can be written as A of t is equal to A of t minus delta t plus delta t times r of t. It's the same as before, but now it's in difference equation form. Instead of t, let's make this t sub I and t sub I minus 1. All right? So from t sub I minus 1, I'm going to predict t sub I, and it's going to be plus delta t times r. And here I played a little trick on you. I made it a little bit tricky, because if I'm at this point and I want to get to this point, all right? There are a lot of different ways of getting from this point to that point. Okay? When you say rate, the rate's going to be changing. Just like the amount's changing, the rate might be changing. You know, in the simple cases we deal with, we might take fixed rates, but the rate can be changing. In which case, if I take the rate over here, which is one thing, I'll get a different result than if I take the rate over here, which is another thing. Not only that, in my calculation, I somehow have to figure I might have to be generating my rate from time to time. So what we do is we take the rate at the midpoint. In other words, I will take my rate at the average of t sub I plus t sub I minus 1 over 2. So I'm taking an average rate, and this is done all over in numerical integrations, where you take something in the middle in order to get a better approximation. If I do this, I know the relationship between t sub I and t sub I plus 1. It's just t sub I is equal to t sub I plus 1 minus 1 plus delta t. So if I put those things in, I get my next relationship over here. That it's r of t sub I minus 1 plus delta t over 2. In other words, it's what I told you. I took my midpoint. There are other algorithms. You can have more complicated things, and there are more complicated algorithms, but they don't really concern you. I will give you advice when needed, when you need fancier algorithms than this, all right? So this is the relationship between the difference equation and the differential equation. In other words, they're both going to give you the same thing, but one I have to know the analytic solution, and the other one, I'm not going to let my delta t go to 0. While I'm on the topic, I mentioned the fact of the size. The size that you take this delta t is going to determine your error. So if you're smart, you say, aha, make delta t very, very small, right? But when you're working on a computer, if you make it very small, then the amount of steps you're going to have to take to get through here is going to be a lot more. So A, will take a lot more time. B, each time there's a extra calculation, the fact of the extra calculation also introduces a little bit of slop on the end of the computer calculation. So you're adding up errors from having too many intervals. And so what you do is you sort of fiddle and get an approximate interval if you have something which isn't changing very much. If I have my r as a constant, then it doesn't matter. If it has a slow slope, it doesn't matter. If I have something which is oscillating wildly, I better take a smaller interval. So there is some judgment calls. In most of what we're doing, our tools and our models are rough enough. Once you've made the body, with all of its organs and all of its blood flow into a single compartment, you don't really have to worry too much about the subtleties. It's only when you do fancier stuff that you'll have to worry about the subtleties. The next page mentions something about R, since I felt I should. Namely, depending what R is, you'll get different models. In one case, I could have R equal to a constant. That would be so-called a one-compartment model with zero order. Or I could have first-order elimination, where my rate of elimination is going to be equal to some rate constant times the amount. Now, this gets trickier. It means you got to know the amount at time t. But that's all right, because I'm going to use the amount at time t, which I know from before, to calculate the amount at t plus 1, so I can use this rate R. This, in a nutshell, if you wish, or any sort of a shell in a pill, I don't know, is a summary of the underpinnings. But I want to emphasize that in doing your modeling, what really counts is having some sort of a intuitive feeling for the subject matter, so that all of what you've seen here, like when should I use a first order model? Well, the answer is, here you are. Here's an intuitive approach to drug in the body. If you look at the fish as drug in the body, and there's your kidney there eliminating them with the net, the amount you're going to eliminate, if you take this analog seriously, is going to be proportional to the amount of fish there. Every time, if you're drawing at a constant rate, if there are a lot of fish, you'll get a lot of fish in your net. As the amount of fish go down, you'll have less fish in your net. This is a perfect example of a rate constant R times the amount at time t. That's going to give you your elimination. So if you can think in physical pictures, and they don't have to be this concrete, but if you can think in physical pictures, you then will be able to formulate what you need. Well, what if you still feel uncomfortable with differential equations? Not to worry. Because if you can think this way, then, and if you can draw things, and you're going to, then using the platform we have, and I know a few of you people saw a quick demo of mine in advanced pharmacokinetics, I can take my compartment where all my stuff is, and that's where the guy's fishing from. It has a certain amount. The guy who's scooping out, that's the loss, and there's going to be a certain parameter, a rate constant, Ke here. All right? If I draw this on the computer, and I have to tell it a few things, I have to tell it what my initial amount is. Makes a difference if it's 10 or more. I'm going to have to tell it what Ke is. But I just draw this on the computer. It's equivalent to writing this differential equation on the bottom. Now, that's pretty neat, because obviously, this one I know how to solve, but obviously, I can put boxes together where I can't solve it. All right? So using this, I'm going to be able to find the solution. What is the computer going to do if I put this together? I'm going to show you what the computer is going to do if I put this together. By putting this together, the program automatically writes some, not all, but some of your equations for you. For example, see this equation? Amount is equal to amount plus dt times minus loss. Well, the amount is just what we said before. Now, it's tiny bit tricky. This is amount at time I plus 1. This is amount at time I. Or this is amount at time I. This is amount at time I minus 1. So amount here, it's anyone who knows any programming, this is the previous value. This is the next value. Plus dt, that's just what we said, that's my delta t, times whatever minus loss, whatever my function is. Now that loss could be a complicated function. I'm going to pick it up somewhere else. This equation got written automatically because of the way you hooked up the diagram that I just showed you. I think that's neat. You have to tell it the initial amount. I said 1 is my initial amount. It won't let you go till you tell it. It's going to give you a question mark. You won't go anywhere. So no brain power involved. You got to do it. I have to define what my loss is. Well, if I know that I want the first order model, I know it's my rate constant times my amount. All right? That's what the guy with the fish was doing. And so I have one more thing to do, namely, I must say what my rate constant is. That's it. It's fully specified. Can't be much easier. Having fully specified it, I then tell the thing run. Show me what will happen with these constants. And in this particular case, this is the solution for exponential decay. So that what do I have here? I have gone through my full modeling, and now I can put in different values. I can see what's going to happen if I change my initial amount, my rate constant, so I can study this ultra-simple system. Now, you're going to try and pick up slightly more complicated systems, which you will study and define and formulate. That's everything that this course is about, from A to Z. So you've gotten an overview of everything, admittedly with a simple example. It reminds me of when I was learning folk dancing. The guy would say, okay, right, left, right. And then the real dance would come, and the music would come, right, 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 all right. So it's a little bit like that also here. You know, I'm going slow and simply. Obviously, life gets a little bit more complex as you struggle with it yourself, but I'll tell you the instructions again next time if you stumble a little bit. So I think you have most of the fundamentals of what we're going to be doing. Any questions?
Secular trends over time,